Look up at the night sky, past the familiar constellations and the serene glow of the moon, and try to picture a point of light so ferociously bright that it outshines not just a single star, but every single one of the hundreds of billions of stars in an entire galaxy. This isn't science fiction. This is the staggering reality of a quasar, one of the most powerful and perplexing phenomena in the entire universe. For decades, since their mysterious flickering was first detected, these objects have captivated and confounded astronomers, presenting a cosmic riddle written in pure, unimaginable energy. They are the ultimate enigmas, blazing from the very edge of observable space, and they force us to confront fundamental questions about the nature of reality itself. What cosmic engine could possibly generate such staggering power? And perhaps more intriguingly, what is its ultimate purpose in the grand architecture of the cosmos? This is not a quiet, academic debate. The questions we ask about quasars sound like they're pulled from the pages of an epic space opera. Are these brilliant beacons natural lighthouses illuminating the vast, dark highways between galaxies? Or are we witnessing the universe's most destructive force, a superweapon of apocalyptic scale? The answer, as we are beginning to understand, might be as profound as it is terrifying, touching on the very life and death of galaxies. This journey will take us to the absolute limits of our understanding, where the laws of physics are stretched to their breaking point. We will sift through the evidence, weigh the competing theories, and grapple with the sheer, humbling scale of these objects. We are about to explore the Quasar Enigma, a mystery that challenges not only what we know, but how we define the possible. So prepare to have everything you thought you knew about the cosmos turned on its head, as we venture into the heart of a light that can travel for billions of years, only to ask us one simple, haunting question: are we looking at a guidepost or a gun? So, to unravel this grand cosmic mystery, we first need to understand the engine at the heart of it all. The term quasar is actually a shortening of quasi-stellar radio source, a name born from pure frustration in the 1950s and 60s. Astronomers, using the first powerful radio telescopes, detected these incredibly bright energy sources. But when they turned their optical telescopes to look, they didn't see a galaxy. They just saw what looked like a single, unassuming star. It was this bizarre contradiction, a thing that blazed with the radio energy of an entire galaxy, yet appeared as a mere pinpoint of light that marked the beginning of the Quasar Enigma. The key to unlocking their secret, however, wasn't found in the brilliant light itself, but in the profound darkness that powers it. Every quasar we have ever discovered is in fact the core of an incredibly distant galaxy. And at the very center of that galactic core lies a supermassive black hole, a gravitational monster with a mass equivalent to millions, even billions, of suns all crushed into a single point. Now, a black hole by itself is just empty darkness. The power, the staggering luminosity, comes from what's happening just outside its point of no return, a region known as the event horizon. Here, vast rivers of gas, dust, and even entire stars are caught in the black hole's irresistible gravitational pull. This material doesn't just fall straight in. Instead, it forms a swirling, frenzied maelstrom called an accretion disk, where particles collide and rub against each other at velocities approaching the speed of light. This unimaginable friction heats the material to temperatures of millions of degrees, causing it to glow with a ferocious intensity that outshines every star in its host galaxy combined. Think of it as the most powerful dynamo imaginable, where gravity's relentless pull is converted directly into pure radiance. This is the beacon we see from across the universe, a light that has traveled for billions of years to reach our telescopes, giving us a direct window into the violent adolescence of the cosmos. It all started with a simple, almost monotonous task: mapping the radio static of the heavens. In the 1950s, astronomers were using the first sophisticated radio telescopes to sweep the skies, creating catalogs of celestial objects that emitted energy in these invisible wavelengths. They kept finding these incredibly powerful, point-like sources of radio waves, but when they aimed their traditional optical telescopes at the exact same coordinates, they saw nothing. Or worse, they saw what appeared to be a perfectly ordinary, faint star. The most logical conclusion was that these were just some strange, local stellar objects within our own Milky Way. They were given dry, clinical names like 3C273, a simple entry in the third Cambridge catalogue of radio sources. But this particular source, 3C273, was about to reveal that it was anything but ordinary. The first major clue was a mysterious jet. Through careful observation, astronomers noticed that this seemingly mundane star had a tiny, faint wisp of material stretching away from it like a thread of luminous silk. This was bizarre. Stars don't have jets like that. The puzzle deepened immeasurably when a brilliant astronomer at Caltech, Martin Schmidt, decided to take a closer look at its light spectrum. Every element in the universe leaves a unique fingerprint of dark and bright lines in the spectrum of light it emits or absorbs. When Schmidt analyzed the spectrum of 3C273, he was utterly baffled. The pattern of lines was completely unrecognizable. It didn't match any known element. For days, he stared at the data until a revolutionary thought dawned on him. What if the pattern was familiar but had been stretched beyond all recognition? This stretching, known as redshift, occurs when an object is moving away from us at tremendous speed, causing its light waves to lengthen and shift toward the red end of the spectrum. The greater the redshift, the faster the object is receding, and thanks to the expansion of the universe, the farther away it is. When Schmidt applied this correction, the mysterious lines snapped perfectly into place, revealing the common signature of hydrogen. But the implications were staggering. The redshift was so immense that it placed 3C273 not within our galaxy, but an almost incomprehensible 2 billion light-years away. For an object at that distance to appear so bright in our sky, it had to be shining with the luminosity of 1 trillion suns. This single calculation shattered the prevailing understanding of the cosmos. It meant this tiny pinprick of light was releasing more energy than every star in its entire host galaxy combined, and it was doing so from a region of space likely no larger than our solar system. The discovery was a scientific earthquake, forcing everyone to completely rethink the limits of physics and cosmic power. This brings us to the dynamo itself, the heart of the quasar that transforms a simple void into the universe's most brilliant beacon. At the core of this entire phenomenon lies a supermassive black hole, an object so gravitationally powerful that its mass is measured not in stars, but in millions, even billions of suns, all compressed into a single point of infinite density. It's a concept that can feel abstract, so let's try to ground it. The supermassive black hole at the center of our own Milky Way, named Sagittarius A, has a mass of about 4 million suns. Now multiply that by 1,000. The black holes powering the most luminous quasars can easily reach masses of several billion solar masses. If you were to place such a monster in the center of our solar system, its event horizon, the point of no return, would extend far beyond the orbit of Pluto, swallowing our entire planetary system whole. Yet, for all their terrifying gravitational might, a black hole sitting alone in the void is just that, a perfect, dark emptiness. It's not the black hole itself that shines, but the frenzied, chaotic demolition derby happening just outside its doorstep. Imagine a vast whirlpool of gas, dust, and shredded stars, all caught in the irresistible pull of gravity. This is the accretion disk, a cosmic traffic jam of apocalyptic proportions where particles are whipped around at nearly the speed of light. The friction generated as this material grinds against itself is so unimaginably intense that it heats the disk to temperatures of millions of degrees. At such extremes, matter doesn't just glow, it screams across the entire electromagnetic spectrum, from radio waves to visible light to high-energy gamma rays, blazing with the light of a trillion suns. This process of converting gravitational potential into raw radiation is staggeringly efficient. While the nuclear fusion that powers a star converts less than 1% of its mass into energy, the maelstrom around a supermassive black hole can achieve efficiencies of up to 40%. This is why a quasar, occupying a space no larger than our solar system, can outshine every single star in its host galaxy for millions of years on end. But the engine has another, even more dramatic exhaust system. Not all the infalling matter is destined for the abyss. Along the black hole's rotational poles, powerful magnetic fields can funnel some of this superheated plasma into two narrow, focused beams. These jets erupt at velocities so close to the speed of light that they are described as relativistic, punching clear through the surrounding galaxy and often extending for hundreds of thousands of light years into intergalactic space. They are the ultimate testament to the raw, focused power of this cosmic generator. So, rather than a simple destructive force, the supermassive black hole is better understood as the universe's most formidable power plant, a gravitational turbine that takes the chaos of falling matter and orchestrates it into the most persistent and brilliant displays of energy we will ever witness. Given our new understanding of this incredible cosmic engine, one of the most profound questions we can ask is a simple one: what is all this power for? Are we witnessing a natural phenomenon with a purpose or something more ominous? Let's first explore the more hopeful, illuminating possibility, the idea of quasars as cosmic lighthouses. Think about the function of a lighthouse on a dark, treacherous coastline. Its brilliant, rotating beam doesn't just warn of danger, it provides a fixed point of reference, a navigational aid that guides ships through the void of the open ocean. In a universe that is overwhelmingly vast and dark, quasars could serve a similar purpose on a literally cosmic scale. Their immense and steady luminosity, visible from billions of light years away, makes them perfect natural signposts. For cosmologists here on Earth, they are already indispensable tools. Because they are so bright, we can detect them at the very edges of the observable universe, giving us a window into the cosmos's infancy. Their light acts like a powerful astronomical backlight. As it travels for eons across the universe to reach us, it passes through the otherwise invisible tendrils of gas and the mysterious halos of dark matter that form the cosmic web, the large-scale structure of the universe. By analyzing how this quasar light is absorbed and filtered, we can literally map this hidden architecture, learning about the material that exists in the vast, empty spaces between galaxies. But let's stretch our imaginations even further into the realm of speculative science. If humanity ever becomes an interstellar species, how would we navigate? Our familiar constellations would be useless, just a jumble of stars from a new vantage point. What we would need are fixed, unmistakable beacons whose positions are constant on a universal scale. The predictable properties and precise redshifts of quasars make them ideal for this. An advanced civilization might use a network of these brilliant objects to triangulate their position in the galaxy, creating a cosmic GPS system built not by engineers, but by the fundamental physics of supermassive black holes. In this view, a quasar is not a weapon of destruction, but an essential piece of celestial infrastructure, a guiding light in the overwhelming darkness that makes the universe navigable and, in a sense, knowable. But this luminous, guiding presence has a far darker twin. Let's flip the cosmic coin and confront the weapon hypothesis, a perspective that transforms the quasar from a celestial lighthouse into the ultimate galactic cannon. Those same relativistic jets, which we admired for their sheer power, become instruments of almost inconceivable destruction when viewed through this ominous lens. These are not gentle beams of light, they are particle streams moving at a significant fraction of light speed, carrying kinetic and radiative energy equivalent to the simultaneous detonation of billions of supernovae. If such a jet were to sweep across a star system, the effects would be apocalyptic. It wouldn't just scorch planets, it would strip away atmospheres, boil away oceans, and bathe every world in lethal levels of radiation, effectively sterilizing entire sectors of space. The scale of this is what pushes the idea into the realm of the terrifying. A quasar's jet can extend for hundreds of thousands of light years, meaning it could, in theory, reach from the center of one galaxy and strike the heart of another. This isn't merely a planet killer, it's a galaxy-altering force. The energy delivered could disrupt the delicate balance of gas and dust within a spiral galaxy, shock compressing some clouds to trigger a firestorm of new star formation, while blowing other star-forming material clear out into the void, effectively halting the creation of new solar systems for eons. The very evolution of a galaxy could be dictated by the aim of a single, distant beam. Now take this natural phenomenon and consider the possibility of conscious control. The most chilling aspect of this theory isn't that a civilization could build such a weapon. The energy requirements are beyond any conceivable engineering, but that an advanced intelligence might learn to harness one. Imagine a species so technologically transcendent that they could nudge the accretion disk of a supermassive black hole, or manipulate its magnetic fields to precisely aim these natural jets. This would be the ultimate expression of power, a cosmic scalpel that could perform galactic-scale surgery or serve as the most formidable deterrent imaginable. In a universe teeming with potential life, the mere knowledge that another civilization possessed the ability to point a quasar in your direction would reshape the entire calculus of interstellar diplomacy and conflict. The quasar, in this terrifying scenario, ceases to be a passive object of study. It becomes an active, loaded weapon on the galactic stage, its silent brilliance a constant, ominous reminder that some forces in the cosmos are not just indifferent, but could potentially be directed with conscious, unimaginable intent. This profound time delay, a direct consequence of the sheer scale of the cosmos, introduces a layer of existential ambiguity to our entire investigation. When you observe the light from a quasar located, say, 2 billion light-years away, you are not seeing it as it is now. You are witnessing a luminous event that actually occurred 2 billion years in the past, and that ancient light has only just finished its marathon journey across the universe to reach our telescopes today. We are, in effect, cosmic historians looking at snapshots from a much more turbulent chapter in the universe's life. The era when quasars were most abundant, often called cosmic noon, was a wild and formative time, roughly 10 to 12 billion years ago, when galaxies were younger, gas-rich, and colliding with one another with far greater frequency. These collisions provided a feast of fresh material to fall into the waiting supermassive black holes at their centers, igniting them into their brilliant quasar phase. The quasars we study most intensely are almost all from this bygone epoch. In our present local universe, most of these brilliant beacons have since gone quiet. Their central black holes still exist, but having consumed or blown away the readily available fuel in their immediate vicinity, they have entered a dormant, quiescent state, like the silent supermassive black hole at the heart of our own Milky Way. This natural life cycle presents the core of our interpretive dilemma. If we are to consider the beacon hypothesis, we are forced to ask, are we intercepting a message from a civilization that flourished billions of years ago, a message whose senders have long since transcended, vanished, or evolved into forms we cannot comprehend? The very act of receiving the signal could be an archaeological discovery, like finding a lost city buried under the sand. The beacon itself might still be shining, a testament to its incredible engineering, but the intelligence that built it may be part of cosmic history. Conversely, the weapon hypothesis becomes even more unsettling through this lens of deep time. If we were to observe a quasar's jet suddenly and precisely swiveling to target another galaxy, we would be witnessing an act of intergalactic warfare that concluded an eternity before Earth's first single-celled organism even appeared. The conflict, the reasons, the victors, and the vanquished, all of it would be ancient history. We would be left with the chilling evidence of a capability for destruction on a scale that defies human understanding, but with no context for its use. This temporal dislocation means that even if we could definitively prove a quasar was being used for a specific purpose, we would be powerless to interact with it or its users. Our search for meaning is inherently a look into a fossil record written in light, forcing us to grapple with the possibility that we are studying the artifacts of gods whose age has long since passed. This inherent variability in quasars, this tendency to flicker and pulse across timescales from mere days to several years, adds a fascinating layer of complexity to the enigma. If you were to monitor a quasar's brightness over time, you wouldn't see a steady, unwavering light like a single star. You'd witness a graph that looks more like the volatile chart of a stock market with unpredictable peaks and valleys. The primary, natural explanation for this flickering lies in the chaotic heart of the accretion disk itself. Imagine trying to predict the flow of water down a vast, raging whirlpool where the inflow is irregular. Clumps of gas and dust of different sizes fall in at different rates, creating turbulence and hotspots that rotate in and out of our view. A particularly large gulp of material, perhaps an entire star that ventured too close and was tidally shredded, can cause a sudden, dramatic surge in brightness. The timescale of the flicker even gives us a rough estimate of the engine's size. Since information cannot travel faster than light, a coordinated brightening across the entire accretion disk can't happen instantaneously. If we see significant changes over a period of days, it implies the active region causing that flare can't be much larger than a few light days across, wonderfully confirming that this immense power is indeed generated in a remarkably compact volume of space. This natural explanation is scientifically robust and fits our understanding of plasma physics and gravity perfectly. Yet, when you introduce the concept of a potential beacon into the conversation, this very same variability transforms from a simple physical process into a potential medium for communication. Think about how we communicate across vast distances here on Earth. We don't use a steady, unmodulated carrier wave for complex information. We modulate it. We alter its amplitude or frequency, imprinting a pattern of ones and zeros onto it to transmit data. From a purely speculative engineering standpoint, if a supremely advanced civilization wanted to create a beacon that was unmistakably artificial, simply making it extremely bright might not be enough. Nature can produce incredible brightness on its own, but imposing a complex, non-random pattern onto that brightness, a pattern that defies natural stochastic noise, would be a potential signature of intelligence. The quasar's own incredible power would provide the energy source, and its stable, long-lived nature would make it a perfect galactic-scale transmitter. The idea, then, is that hidden within the seemingly random flickering of a quasar's light curve, there could be a structured, repeating signal, a cosmic QR code written in fluctuations of pure energy. Scientists, often driven by curiosity as much as skepticism, have actually taken this idea seriously enough to investigate. Through projects loosely affiliated with the Search for Extraterrestrial Intelligence, or SETI, researchers have applied sophisticated mathematical and computational analyses to the light curves of quasars, searching for non-random patterns, prime number sequences, or any signature that cannot be explained by known physics. The results so far have been unequivocal. No such intelligently engineered signal has ever been detected. The variations always conform to the kind of chaotic noise and red noise expected from a turbulent, natural physical system. While the notion of a message hidden in the most powerful light in the universe is a breathtakingly beautiful and cinematic concept, the evidence firmly points away from it. The flickering remains a powerful and eloquent testament to the violent, chaotic, and beautifully natural processes governing matter in its most extreme state, not a whisper from a distant engineer. To truly grasp the sheer, focused power behind a quasar's jet, we need to peer beyond the glow of the accretion disk and into the invisible architecture that shapes it. While gravity pulls the material in, it is another, far more organized force that orchestrates its most spectacular exit: magnetism. The spinning, superheated plasma of the accretion disk acts like a dynamo on a cosmic scale, generating magnetic fields of almost inconceivable strength. These aren't the gentle fields that guide a compass needle. They are magnetic hurricanes, tangled and intense, woven through the chaos. And it is within this magnetic maelstrom that the universe's most efficient particle accelerator is born. Picture the process not as a simple explosion, but as the operation of a perfect cosmic railgun. In a human-made railgun, electrical currents and magnetic fields work in concert to propel a projectile to incredible velocities. Around a quasar, the physics is similar but magnified to an almost unimaginable degree. The black hole's immense rotation, coupled with the frantic spinning of the accretion disk, twists these magnetic field lines into a tightly wound helical structure. Charged particles, electrons and protons caught in the flow, get caught on these field lines like beads on a wire. They are then whipped along, funneled by the magnetic pressure away from the disk and up along the black hole's rotational poles, accelerating to a staggering 99.9% of the speed of light. This is the secret to the jet's incredible collimation, its needle-like straightness over hundreds of thousands of light years. Without these magnetic fields, the energetic particles would simply expand outward in a diffuse, ineffective cloud like smoke from a candle. Instead, the magnetic fields act as a rigid sleeve, a focusing mechanism that prevents the jet from dispersing and keeps its devastating energy locked into a narrow, coherent beam. The precision of this natural engineering is humbling. It achieves a level of focus and efficiency that our greatest particle accelerators and directed energy weapons can only dream of, all orchestrated by the fundamental laws of physics in one of the most extreme environments possible. When we consider the beacon hypothesis, these magnetic fields become the essential stabilizer. A lighthouse with a flickering, unfocused beam is useless for navigation. For a quasar to serve as a reliable cosmic signpost, its light, and particularly the focused radio emission from its jets, needs to be steady and predictable. The magnetic fields provide that stability. They regulate the flow of material into the jets, maintaining a consistent output that could, in theory, be relied upon for eons by any civilization using it as a fixed point in the void. The longevity and coherence of the jet are direct products of this magnetic confinement, making the quasar not just a brilliant flash but a persistent and dependable signal. Now shift your perspective to the weapon hypothesis, and the role of magnetism transforms from a stabilizer into a targeting system. The sheer destructive potential of a quasar's jet is only realized because of its incredible focus. A diffuse cloud of energy, no matter how powerful, would lose its punch over intergalactic distances, but a magnetically collimated beam does not. It maintains its intensity, allowing it to deliver a catastrophic dose of radiation and kinetic energy across millions of light years with pinpoint accuracy. In this terrifying scenario, the magnetic fields are the scope and the barrel. An intelligence that could learn to manipulate these fields, to adjust their alignment by even a tiny fraction of a degree, would possess the ability to aim this galactic-scale cannon. The study of this entire process falls to a branch of physics known as magnetohydrodynamics, or MHD, the science of how magnetic fields interact with electrically conducting fluids like plasma. For astronomers, MHD is the key that unlocks the behavior of quasar jets. The mathematical models we use to simulate them are complex and breathtakingly detailed, and so far, every observation we have, from the jet structure to its polarization, fits perfectly within the framework of natural MHD. There is no need to invoke an external engineer to explain the stunning precision. The universe, through the pure, unguided application of physical law, is capable of engineering this phenomenon on its own. This brings us to a profound crossroads of interpretation. We are left observing a system of such immense power and perfect focus that it appears, for all intents and purposes, engineered. Yet the underlying physics requires no engineer. This is the core of the Quasar Enigma. It forces us to confront a deeply unsettling question. At what point does a natural phenomenon become so efficient, so precise, and so powerful that it is indistinguishable from a deliberately constructed tool? To truly grasp the staggering power we're discussing, it helps to compare it to another cosmic cataclysm we often view as the ultimate benchmark for destruction, the supernova. A supernova is, without question, one of the most violent and brilliant events in the universe. In a matter of days, a single dying star can unleash so much energy that it briefly rivals the combined light of every other star in its entire galaxy. It's a spectacular final farewell. Yet, when we place this phenomenal event next to a quasar, the difference isn't just a matter of degree, it's a difference in kind. Imagine the brightest flash of lightning you have ever seen, a burst so intense it illuminates the entire landscape for a split second. That is a supernova. Now, imagine a sun so brilliant and constant that its light never fades, a permanent star shining with the intensity of 1,000 lightning flashes happening every second for millions of years on end. That is a quasar. The numbers are almost impossible to internalize. A typical supernova might release something on the order of 10 to the 44 joules of energy in its brief, weeks-long peak. A quasar, by contrast, can steadily emit energy at a rate of 10 to the 40 joules every single second. Over the course of a single year, a quasar can therefore radiate more energy than a supernova releases in its entire explosive event. And quasars keep up this relentless output not for years, but for millions, sometimes tens of millions of years. When you sum up the total energy a single quasar liberates over its entire active lifetime, it can easily dwarf the combined energy of every single supernova that has ever exploded or ever will explode across the entire history of its host galaxy. This isn't just a more powerful firework, it's the difference between a firecracker and the continuous, focused fury of the sun itself. This comparison is what gives the weapon hypothesis its chilling plausibility. A supernova is an indiscriminate blast, a cosmic bomb. But a quasar, with its focused jets and unimaginable longevity, represents something far more potent, a sustained and directed force. The energy available isn't just for a single, catastrophic blow. It's enough to reshape the destiny of an entire galaxy over cosmic timescales. A quasar's jet channeling this power could act as a persistent scalpel, not just a hammer. It could strategically heat vast reservoirs of galactic gas, preventing them from cooling and collapsing to form new stars, effectively sterilizing a galaxy of future planetary systems over eons. It could trigger star formation in one spiral arm while quenching it in another, sculpting the galactic structure itself. The sheer duration of its output means the quasar isn't just a momentary threat. It is a permanent, looming presence on the galactic stage, a force capable of guiding evolution on a scale that transcends biology and enters the realm of astrophysics. This search for an intelligently engineered pattern is perhaps the most rigorous test we can apply to the quasar phenomenon, and it takes us directly into the methodology of the search for extraterrestrial intelligence. The core principle of SETI is elegant in its simplicity. Nature is noisy and chaotic, while technology, by its very nature, imposes order. Therefore, the definitive signature of an artificial signal would be the presence of something that cannot be produced by any known natural process. This usually means looking for one of two things: either a signal that is impossibly narrow in its frequency, like a pure, unwavering radio tone, or a signal that carries a complex, non-random pattern imprinted upon it. It's the difference between the sound of ocean waves crashing on a shore, a beautiful but stochastic roar, and the precise, structured rhythm of a drumbeat, or even more tellingly, a sequence of prime numbers. This logic has been directly applied to quasars. Teams of researchers have taken the light curves of these objects, the detailed graphs of their brightness over time, and subjected them to the most sophisticated statistical analyses imaginable. They've searched for hidden periodicities, for intricate sequences, for any form of modulation that would suggest a mind was behind the flickering, and they have found something, but not what they were looking for. Many quasars exhibit what are known as quasi-periodic oscillations. These are flickers that appear to have a rough, underlying rhythm, with brightness peaks recurring every few hours, days, or even years. For a moment, this might sound promising, a repeating pattern, but when astrophysicists modeled the chaotic environment of the accretion disk, they found a perfect, natural explanation. The key lies in orbital resonances. Think of it like pushing a child on a swing. If you push at just the right moment in the swing's arc, you add a little energy each time, and the swing goes higher and higher. In an accretion disk, the swirling gas doesn't orbit at a single uniform speed. Material closer to the black hole orbits much faster than material farther out. At specific distances, these orbits can fall into a gravitational resonance, where the orbital periods are simple ratios of each other, like 2 to 1 or 3 to 2. These resonances can create stable, high-pressure regions that periodically dump more material into the inner disk, causing a regular brightening. It's a complex physical process, but a thoroughly natural one, driven purely by gravity and orbital mechanics. The quasi-periodic oscillations we observe match these models with remarkable precision, effectively closing the door on the idea that these specific rhythms are a form of communication. The conclusion from decades of this painstaking analysis is unambiguous. No evidence has ever been found for a structured, information-rich signal hidden within a quasar's light. Every fluctuation, every pulse, and every quasi-rhythm can be explained by the known, if extreme, physics of superheated plasma and immense gravity. And yet, to declare the case completely closed would be premature, verging on arrogance. The universe has a way of humbling our assumptions. One profound challenge is the sheer number of quasars. We have identified hundreds of thousands of them, but that is likely a tiny fraction of the total that have ever existed. It is statistically possible, however unlikely, that a signal exists in a quasar we haven't studied in sufficient detail, or one whose specific pattern we are not yet clever enough to recognize. Furthermore, we must confront the indistinguishability problem. Our entire search strategy is predicated on the idea that an artificial signal will look obviously unnatural. But what if a civilization is so profoundly advanced that its technology is seamlessly integrated with nature? Their concept of engineering might be so refined that it produces signals that are, for all intents and purposes, identical to natural astrophysical processes. Their ultimate beacon might not be a flashing sequence of prime numbers, but a perfectly stable, seemingly natural light source with properties so finely tuned that its very perfection is the signature. We wouldn't be looking for an anomaly, we'd be looking for an ideal. From this perspective, the most powerful argument for the natural origin of quasars, that they behave exactly as physics predicts they should, could, in a dizzying twist, be reinterpreted as the ultimate testament to a technology so advanced it has become indistinguishable from the laws of the universe itself. This cosmic interplay of light and gravity gives us one of the most powerful tools in all of astronomy, a phenomenon predicted by Einstein over a century ago: gravitational lensing. His theory of general relativity revealed that space-time isn't a static stage but a flexible fabric, warped by the presence of mass. Just as a heavy ball placed on a stretched rubber sheet would create a dip, a massive object like a galaxy or a galaxy cluster bends the very fabric of space around it. When light from a distant object like a quasar travels through this warped region, its path is no longer straight. It follows the curvature, meaning the massive object in between acts like a giant cosmic lens, distorting and magnifying the light from the source behind it. The effects can be breathtakingly dramatic. Instead of seeing a single quasar, we might observe multiple shimmering copies of it arranged in a perfect arc or a cross around the foreground galaxy, a configuration known as an Einstein ring or cross. Other times, the lensing doesn't create multiple images but acts as a pure magnifying glass, amplifying the quasar's brightness by a factor of 10, 50, or even more. For astronomers, this is like being handed a free, universe-made telescope. It allows us to peer into the inner workings of a quasar's engine with a level of detail that would be utterly impossible from our vantage point in the cosmos. We can study the fine structure of its accretion disk and even map the distribution of mysterious dark matter in the foreground lensing galaxy, because it is the gravity from all the mass, both visible and dark, that creates the lensing effect. This natural magnifying process is indispensable for pushing the boundaries of observational science. Now, let's view this through the lens of our central enigma. If a quasar were to function as a beacon, gravitational lensing transforms from a handy observational tool into a potentially deliberate component of a galactic-scale communication system. Think of it like using a satellite dish to focus a faint television signal from a distant broadcaster. The signal exists, but without the dish to collect and concentrate the waves, it's too weak and diffuse to be of any use. In this speculative framework, a naturally occurring gravitational lens could serve the exact same purpose for a quasar's light. An advanced civilization wouldn't need to build a lens spanning light years. They could simply use the one the universe has already provided. By positioning their receiver at the precise focal point of this natural gravitational lens, they could receive a massively amplified and clarified version of the quasar's signal, turning a faint whisper into a roaring, crystal-clear broadcast. The utility is undeniable. It would make an already brilliant beacon exponentially more effective across mind-boggling intergalactic distances. This introduces a fascinating layer of cosmic real estate. The most valuable location in a galaxy for an observatory, or perhaps for a listening post, might not be a planet with a clear atmosphere, but a specific point in empty space where the gravity of a neighboring galaxy perfectly focuses the light from a distant quasar, creating the universe's most powerful signal booster. While we have absolutely no evidence that this is happening, the mere fact that the physics allows for it adds a profound dimension to the mystery, suggesting that the cosmos might be threaded with these naturally occurring communication channels waiting to be discovered. This line of inquiry brings us face to face with one of the most haunting questions in all of science, the Fermi paradox. Enrico Fermi famously captured its essence with a simple, devastating query. If the universe is so vast and old, and the ingredients for life are seemingly everywhere, then where is everybody? The profound and unsettling silence we observe, the absence of any definitive signal or artifact, stands in stark contrast to the statistical probability of other intelligent beings. The distribution of quasars throughout cosmic history offers a potential and deeply sobering clue to resolving this paradox. We now understand that the universe went through a kind of quasar heyday between 10 and 12 billion years ago. This was a wild, formative period when galactic collisions were frequent, gas was plentiful, and supermassive black holes were feasting, lighting up the cosmos in a brilliant fireworks display. Since that peak, the number of active quasars has plummeted. The universe has quieted down, matured, and settled into a more stable and far less luminous middle age. If we entertain the possibility that these objects were not entirely natural, this timeline becomes incredibly significant. It suggests that the era of cosmic-scale engineering, the age of civilizations capable of harnessing or creating such phenomenal power, may have been a specific phase in the evolution of intelligence, one that has largely concluded. The great silence we experience today wouldn't be a sign that we are alone, but rather that we are latecomers to the galactic stage. We are like a civilization emerging on Earth thousands of years after the fall of a mighty, globe-spanning empire, wandering among the overgrown ruins and wondering why the world is so quiet, oblivious to the grand drama that already played out. The most powerful actors in the cosmic story may have already had their moment, their era of brilliant beacons and potential conflict, and have since moved on, either transcending to a state we cannot perceive or succumbing to the very forces they wielded. This perspective fundamentally reframes our search for meaning. We are not listening for our cosmic contemporaries. We are sifting through the archaeological remnants of a bygone golden age. The quasars we study so intently are not active tools, but the dormant, cooling artifacts of technologies and intentions that are now part of the universe's deep history. This idea connects the Quasar Enigma directly to the concept of transcension in astrobiology, the hypothesis that advanced intelligences don't colonize space in a way we would recognize, but instead evolve beyond physical form, perhaps by uploading their consciousness into simulated realities or harnessing the energy of black holes in ways that render them invisible to our current method. Detection. In this view, a quasar could represent the adolescence of a civilization, a spectacular and powerful but ultimately transitional phase of growth. Once a society achieves a certain level of mastery over matter and energy, the need for colossal, galaxy-spanning beacons or weapons might simply vanish, replaced by technologies that are far more subtle, efficient, and undetectable to a young species like ours, still listening for radio waves and looking for the glow of Dyson spheres. We are, in effect, searching for smoke signals in a world that has long since moved on to fiber optics. The quiet cosmos is not empty. It is simply populated by entities that have graduated to a conversation we are not yet equipped to hear, leaving behind the brilliant, fossilized remnants of their own fiery youth for us to discover and ponder. Applying the principles of information theory to the Quasar Enigma gives us a completely new set of criteria to judge whether we're looking at a beacon or a weapon. At its core, information theory is the science of how messages are encoded, transmitted, and decoded, and its most crucial metric is the signal-to-noise ratio. A signal that is meant to be understood must be clear and distinct from the random background static of the universe. From this standpoint, a quasar is an absolute marvel. Its sheer, raw power gives it an astronomical signal-to-noise ratio by default, making it detectable across billions of light years. It cuts through the cosmic haze with an authority that no human-made transmitter could ever hope to match. If your primary goal is simply to be seen, to announce your presence with a flash of light that says, "We are here," then a quasar's natural output is phenomenally effective. It's the ultimate attention getter, but when we move from simple detection to the transmission of complex information, the quasar's natural properties become far less ideal. The light from a quasar is what's known as broadband emission. It isn't a single, pure frequency. It's a cacophony, a roaring torrent of energy spread across the entire electromagnetic spectrum, from long radio waves to incredibly energetic gamma rays. For sending a detailed message, a mathematical constant, a biological blueprint, or a historical archive, this is an incredibly inefficient method. Think of it like trying to have a deep, nuanced conversation in the middle of a roaring heavy metal concert. The power is there, but the clarity is lost in the noise. A civilization with the technological prowess to deliberately create such a beacon would almost certainly choose a more sophisticated method. They would use a narrowband signal, a laser-like beam of information concentrated into a very specific, unnatural-looking frequency. This would be the cosmic equivalent of a whisper that carries for light years, a signal that is both powerful and information-rich, with a structure that screams artificial. The fact that we do not see this in quasars is a strong point against the deliberate beacon hypothesis. Now, flip the perspective to the weapon scenario, and the broadband, noisy nature of quasar emissions suddenly becomes a perfect fit. A weapon of galactic-scale destruction doesn't need to carry a complex message. Its only message is the delivery of raw, concentrated energy. The purpose isn't to be decoded, but to destroy. The broadband output is actually an advantage here. A narrowband, focused energy weapon might be more efficient, but it could also be more easily defended against or dissipated over intergalactic distances. A broadband blast, however, delivers a devastating shockwave of energy across multiple wavelengths simultaneously. It would be far more difficult to shield against, as it would overwhelm defenses with heat, radiation, and kinetic force all at once. The chaotic, turbulent nature of the quasar's accretion disk, which makes it so noisy and inefficient for communication, is precisely what would make it such a formidable and indiscriminate area denial weapon. The very properties that argue against a refined beacon align almost perfectly with the profile of a weapon of immense and terrifying power. Yet we must entertain one final, deeply mind-bending possibility. What if the seeming imperfection is actually the ultimate sophistication? An intelligence so advanced that it wishes to remain hidden might deliberately design its beacon to mimic a natural phenomenon with impeccable precision. In this scenario, the broadband noise isn't a flaw, it's a camouflage. The real, complex signal could be hidden in plain sight, perhaps encoded in the subtle correlations between different wavelengths or in the quantum fluctuations of the light itself, using a cipher so advanced that to our current technology, it is indistinguishable from random noise. The beacon wouldn't be meant for a species at our level of development. It would be a message for peers, for other civilizations that have reached a similar transcendent understanding of physics, who know exactly what to look for. From this dizzying vantage point, the very fact that quasars behave exactly as natural astrophysics predicts could be the most clever and chilling disguise of all. Contemplating the weapon hypothesis forces us to confront a terrifying and profound ethical landscape, one where morality is no longer measured on a human scale but on a galactic one. The sheer power involved is so immense that its application would be less like a declaration of war and more like a force of nature, an act of cosmic terraforming, or more accurately, galactic-scale gardening. A civilization wielding such a tool wouldn't be targeting individual worlds, it would be managing entire ecosystems of stars. Imagine the motivation, perhaps to maintain a stable, quiet region of space for their own unfathomable purposes, to prevent the chaotic rise of potential competitor species, a sort of preemptive pruning of the galactic tree of life, or even to reshape the flow of interstellar gas to suit their long-term energy needs. This isn't a weapon of conquest in any sense we understand. It's a tool for enforcing a particular cosmic order, a means of ultimate control over the very process of evolution itself. The ethical framework required to make such a decision is utterly alien to our own. From our human perspective, the deliberate sterilization of thousands, perhaps millions, of potential worlds is an act of unspeakable horror, the ultimate crime against life. Yet, for a civilization that thinks in terms of billions of years and the lifespan of galaxies, our moral outrage might seem as quaint and parochial as a bacterium objecting to an antibiotic. Their calculus could be one of long-term stability versus short-term chaotic proliferation. They might see nascent life not as something to be nurtured, but as a potential future virus threatening the health of the galactic body, a risk that must be neutralized for the greater, unimaginable good of their own continued existence. This line of thought leads us directly to one of the most chilling potential resolutions to the Fermi paradox, the unsettling question of why the universe seems so silent. Perhaps the great silence is not a result of life's rarity, but of its success. The most advanced civilizations may not be the noisy, expansionist explorers we often imagine. Instead, they could be quiet, patient, and deeply conservative cosmic gardeners. Their primary activity isn't broadcasting their presence or building glittering empires, but meticulously maintaining their local galactic environment. They would operate with a principle of supreme stealth, ensuring their existence leaves no detectable trace. In this dark scenario, a quasar, or the controlled manipulation of one, isn't a beacon of glory but the ultimate weeding tool, used to clear out overgrown, noisy patches of the galaxy before any potentially troublesome intelligent life can emerge and challenge their quiet dominion. We don't see them because they don't want to be seen, and the evidence of their gardening might be all around us, written in the unexplained distribution of dead galactic zones or the mysterious absence of life in regions that otherwise seem perfectly hospitable. We might, in fact, be living in a part of the cosmos they have already pruned and deemed suitably quiet, or perhaps we are simply too primitive and remote to have yet attracted the attention of the galactic groundskeepers. This transforms our search for cosmic companionship from a hopeful endeavor into a perilous one, suggesting that making ourselves known could be the single most dangerous act in human history. To truly appreciate the scale of what we're contemplating, we need a framework, a way to classify civilizations that stretches our imagination to its breaking point. This is where the Kardashev scale comes in, a brilliant thought experiment devised by the Soviet astronomer Nikolai Kardashev in the 1960s. It's not a blueprint, but a way of categorizing technological advancement based on one simple, universal metric: energy consumption. A Type 1 civilization has mastered its home planet, harnessing all the energy that falls on its world from its parent star. A Type 2 civilization has outgrown its planet and now commands the entire energy output of its star, perhaps by constructing a theoretical Dyson sphere. And then, at the very peak of this conceptual ladder, sits the Type 3 civilization. This is an intelligence that has transcended its home solar system and achieved dominance over its entire host galaxy, capable of utilizing the energy equivalent of every single star within it. The leap from Type 2 to Type 3 is not just incremental, it is the difference between managing a single household and governing an entire continent. The energy budgets involved are so vast they defy human comprehension. When we hold this theoretical standard against the raw, unbridled power of a quasar, the alignment is not just striking, it's almost unnerving. A quasar's luminosity can easily reach a significant percentage of the total starlight produced by an entire galaxy. To control, or even more incredibly, to create such an object would be the definitive signature of a Type 3 civilization. It would be the ultimate statement, a project that redefines the very meaning of engineering. We're not talking about building cities or starships anymore. We are talking about galactic-scale architecture, about forging the most powerful engines in the universe and bending them to a will. The concept of a Dyson sphere, a megastructure encapsulating a star, feels almost quaint in comparison. A civilization capable of quasar-level engineering would be operating on a plane of existence where entire star clusters become building blocks, and supermassive black holes are not objects of terror but tools to be wielded. The sheer logistics are mind-boggling. How would you even begin to feed a supermassive black hole on a schedule? The answer might lie in a level of celestial mechanics we can barely glimpse, such as the deliberate orchestration of galactic mergers to funnel entire streams of gas and stars into the central engine, or the development of technologies that can stabilize the chaotic accretion disk, turning a violent, sputtering dynamo into a steady, reliable power source. This perspective forces a profound and deeply unsettling reinterpretation of the cosmos. For centuries, astronomers have worked under the guiding principle that the universe is governed by natural, impersonal laws, and that our task is to simply observe and understand those laws. But what if, when we look at the most extreme phenomena, we are not just seeing nature? What if we are seeing the artifacts of an intelligence so profoundly advanced that its technology has become seamlessly, perfectly integrated with the laws of physics? Their engineering wouldn't look like clanking metal and blinking lights. It would look like astrophysics. Their greatest achievements would be indistinguishable from the natural life cycle of galaxies. This is the final, dizzying frontier of the Quasar Enigma. It challenges the very foundation of scientific inquiry, forcing us to ask whether there even is a clear line between a supremely advanced technology and nature itself. We are left staring at a point of light that has traveled for billions of years, holding two equally staggering possibilities in our minds: that we are witnessing a spectacular but natural cosmic event, or that we are looking at the enduring signature of a consciousness that has learned to write its name in the fabric of space-time with the power of a galaxy. And yet, for all the spine-tingling intrigue of cosmic lighthouses and galactic superweapons, the most compelling explanation for quasars may be one that requires no intelligence at all, but is instead written into the very DNA of how galaxies live and die. This is the narrative of cosmic ecology, a story where quasars are not tools wielded by some unseen hand, but fundamental, natural forces that regulate the growth and health of the universe itself. Imagine a vast cosmic forest. In any healthy forest, you need processes for both growth and renewal. You need fertile soil and sunshine to nurture new trees, but you also need the occasional wildfire to clear out the underbrush, recycle nutrients, and prevent the entire system from becoming choked and stagnant. In this grand analogy, the cold gas scattered throughout a galaxy is the fertile soil, the raw material from which new stars and solar systems are born. The supermassive black hole at the galactic center is not a sleeping monster, but the potential source of the wildfire. And the quasar is the fire itself, a brilliant, cleansing conflagration that fundamentally reshapes its environment. The trigger for this cosmic fire is often a galactic merger, when two gas-rich galaxies collide in a slow, gravitational dance spanning hundreds of millions of years. Their orderly structures are violently disrupted. Vast reservoirs of gas that were once peacefully orbiting in the outskirts are thrown off their courses, funneled inward by immense gravitational tides directly toward the waiting central black holes. This is the feast that ignites the quasar. The resulting blaze does two critical things. First, the intense radiation and powerful winds blowing out from the accretion disk blast through the surrounding galaxy. This energetic feedback heats up the remaining galactic gas, preventing it from cooling, collapsing, and forming new stars. It's a self-regulating brake on galactic growth. The black hole, in a sense, limits its own future food supply and prevents the galaxy from burning through all its fuel in a short, furious burst of star formation. Second, those spectacular relativistic jets act on an even larger scale. They punch out of the galaxy and into the vast intergalactic medium, the thin soup of gas that fills the space between galaxies. By heating this material, the jets prevent it from cooling and falling back into the galaxy, effectively cutting off the external supply of star-forming fuel. This process is crucial for explaining why we don't see many enormous, star-bloated galaxies in the modern universe. The quasars of the ancient past effectively put a cap on how big a galaxy can grow. This natural narrative is not just an elegant theory, it's supported by a mountain of observational evidence. We have stunning telescopic images that catch galaxies in the act of merging, their distorted shapes often hosting a brilliantly shining quasar at their very heart. Computer simulations that model the physics of gravity, gas dynamics, and black hole growth consistently show that these mergers naturally produce the quasar phenomena we observe, complete with powerful jets and winds. The life cycle is clear, a period of violent quasar-fueled activity that regulates the galaxy's growth, followed by a long, quiet maturity as the central engine, starved of fuel, falls dormant. Our own Milky Way, with its quiet central black hole, is a testament to this late, tranquil phase of life. In this cosmic ecological view, the quasar is not a beacon or a weapon. It is a vital, natural, and inevitable phase in the life of a galaxy, a brilliant, transformative fire that shapes the cosmos into the structured, diverse universe we observe today. But just as we think we have a handle on the mechanics, a ghost enters the machine, a shadowy component that could rewrite our entire understanding of these cosmic engines. We've been talking about the power generated by superheated, visible matter, the gas, dust, and stars that we can see falling into the black hole. Yet we know with near certainty that this luminous, familiar matter accounts for less than 20% of the total gravitational pull holding galaxies together. The rest, the overwhelming majority of the universe's mass, is made of something we cannot see, something that does not emit or absorb light, dark matter. This mysterious substance forms vast, spherical halos around every galaxy, including our own, and its gravitational influence is the primary architect of the cosmic web. So it's only logical to ask, what is dark matter's role in the quasar phenomenon? Could this invisible scaffolding be secretly fueling the most brilliant lights in the cosmos? The answer, emerging from the frontiers of theoretical physics, is a tentative but fascinating maybe. One compelling idea suggests that certain hypothetical types of dark matter particles, known as weakly interacting massive particles or WIMP, could behave in a unique way at the very centers of galaxies. Drawn in by the immense gravity of the supermassive black hole, these particles would reach incredibly high densities. According to the theory, when a WIMP collides with its antimatter counterpart, the two would annihilate each other in a flash of pure energy, converting their entire mass into radiation as per Einstein's famous equation. This process could provide a potent, steady, and previously unaccounted for energy source right at the heart of the quasar engine. It wouldn't replace the power from the accretion disk, but it could act as a constant, underlying power booster, a hidden furnace that helps explain certain aspects of a quasar's long-term stability and incredible output. This isn't just a minor tweak to the model, it's the potential discovery of an entirely new power source operating in the universe's most extreme environments. Another, more subtle possibility involves dark matter's gravitational influence on the accretion disk itself. We picture these disks as flat, pancake-like structures of hot gas, but their formation and stability are delicate dances between gravity, rotation, and pressure. The invisible halo of dark matter permeating the galaxy exerts its own gravitational pull, a gentle but pervasive tide that could subtly influence how the disk forms, how stable it remains over millions of years, and even how efficiently it channels material into the waiting black hole. Dark matter might act as a hidden director, orchestrating the flow of ordinary matter from the shadows and ensuring the cosmic engine runs smoothly for eons. Now let's connect these theoretical threads to our central enigma. The standard beacon and weapon hypotheses are built entirely on our understanding of normal matter physics. But if dark matter is indeed an active participant, it introduces a profound and unsettling unknown. The very nature of dark matter is one of the greatest unsolved problems in all of science. We know it has gravity, but we do not know if it interacts with itself or with normal matter in any other way. This vast realm of ignorance leaves the door wide open for exotic possibilities. What if an advanced intelligence, one that has somehow decoded the true nature of the universe's hidden mass, learned not just to harness a black hole, but to manipulate the dark matter halo surrounding it? The ability to control this invisible framework would grant a level of power that makes engineering an accretion disk seem primitive. You could, in theory, regulate the fuel supply to the central black hole by manipulating the dark matter's distribution, turning the quasar's brilliance up or down like a celestial dimmer switch. You could stabilize or destabilize the entire galactic core from a distance, using the dark matter as a gravitational tool. the weapon potential becomes even more chilling. A civilization that could somehow ignite a dense concentration of dark matter particles for annihilation could trigger a quasar-like outburst without needing a major influx of normal gas, creating a brilliant and destructive flash on demand in an otherwise quiet galaxy. This transforms dark matter from a passive component into a hidden variable, a secret layer of complexity in the Quasar Enigma that we are only just beginning to grasp. While there is currently no direct evidence to support these speculative leaps, their possibility underscores a humbling truth. Our search for meaning in the cosmos is limited by the boundaries of our own knowledge. The ultimate answer to the Quasar Enigma may not lie in the brilliant light we see, but in the profound darkness we are still striving to understand. Venturing into the most fundamental layer of reality, we encounter a realm where our conventional understanding of physics breaks down entirely, replaced by the bizarre and counterintuitive rules of quantum mechanics. Here, at the very precipice of the event horizon, another astonishing process unfolds, one that challenges the classical notion of a black hole as a perfect, one-way street into oblivion. This is Hawking radiation, a theoretical prediction made by the legendary physicist Stephen Hawking. He demonstrated that the vacuum of space is not truly empty, but is a seething, frothing sea of virtual particles. These particle-antiparticle pairs constantly pop into and out of existence, borrowing energy from the universe for a fleeting moment before they annihilate each other and pay back the debt. Now, imagine this happening right at the edge of a black hole's event horizon. If one of these virtual particles falls in while its partner escapes, the one that escapes becomes real, stealing a tiny amount of the black hole's mass energy in the process. This slow, steady trickle of radiation causes the black hole to gradually evaporate over astronomically long timescales. For a supermassive black hole powering a quasar, this Hawking radiation is so incredibly faint, so utterly minuscule compared to the roaring inferno of the accretion disk, that it is completely undetectable and physically insignificant. It's like trying to hear a single snowflake land in the middle of a thunderous rocket launch. From a purely natural standpoint, it is a fascinating theoretical footnote, but one with no practical bearing on the quasar's immense power. However, when we shift our perspective to the speculative realm of technology that could be wielded by a Type 3 civilization, this negligible whisper transforms into a potential paradigm. The core of Hawking's discovery is that this radiation is not random noise. According to some resolutions of the black hole information paradox, it may carry with it a scrambled but complete record of all the information about every particle that ever fell into the black hole. In essence, the event horizon could be performing the universe's most extreme data compression, encoding the entire history of its consumption into its outgoing radiation. An intelligence that could decode this radiation would possess a complete log of everything the black hole had ever consumed. This turns the black hole from a simple engine into the ultimate cosmic archive. But the implications for communication are even more staggering. If information can be encoded into the Hawking radiation, then the event horizon itself becomes a potential quantum transmitter. An advanced technology might not need to manipulate the turbulent accretion disk. It could instead operate on the quantum foam at the Planck scale, perhaps by using focused energy beams to influence which virtual particles are created and which ones escape. The transmitted signal would be fundamentally quantum in nature, potentially carrying information through quantum entanglement, allowing for instantaneous communication across any distance, a concept that would make even our most advanced fiber optic networks seem like tin cans and string. The signal would be imprinted on a carrier wave that is intrinsically linked to the black hole's own quantum structure, making it a beacon that is not just bright, but fundamentally inseparable from the fabric of space-time itself. This would be the ultimate stealth communication channel. To any observer without the quantum key to decode it, the signal would be indistinguishable from the natural thermal Hawking radiation, a background hiss so quiet it's drowned out by the cosmic microwave background. There would be no modulating brightness, no rhythmic pulsing to give it away. The beacon would be hidden not in the light, but in the quantum vacuum fluctuations at the very edge of reality. This concept pushes the Quasar Enigma to its absolute limit, forcing us to consider that the line between a natural phenomenon and an advanced technology may not be drawn in the sand of energy output or observable structure, but in the invisible ink of quantum information. We are left with the humbling realization that the most profound signatures of intelligence in the cosmos might not be written in light at all, but in the subtle, quantum-scripted evaporation of a singularity, a message so advanced we currently lack not just the receiver, but the very conceptual framework to even recognize it as a message. Even with all our theoretical brilliance and deep cosmic pondering, we are ultimately bound by a simple physical limitation: the quality of the observations we can make from our tiny perch in the cosmos. For decades, our vision has been guided by incredible instruments like the Hubble Space Telescope and the Chandra X-ray Observatory. Hubble has provided stunning visible and ultraviolet images of the host galaxies that cradle these brilliant quasars, while Chandra has peered through the obscuring dust to see the high-energy X-rays screaming from their furious accretion disks. These telescopes have been our primary windows, confirming the basic model and revealing the colossal scale of the jets. Yet they are like trying to study the fine brushstrokes of a masterpiece painting from 100 feet away. You can see the grand composition, but the crucial, defining details remain frustratingly blurred. The immense distances involved, the obscuring clouds of cosmic dust, and the sheer faintness of the most ancient quasars have placed a hard ceiling on our understanding. We have been assembling the puzzle with many of the most important pieces still missing. This technological barrier is precisely why the next generation of observatories isn't just an incremental upgrade. It represents a fundamental leap in our perceptual abilities, a chance to move from seeing blurry silhouettes to reading the cosmic fine print. The two most anticipated instruments in this new vanguard are the James Webb Space Telescope and the Square Kilometre Array, each designed to attack the problem from a completely different yet complementary angle. The James Webb Space Telescope, or JWST, is our new infrared eye in the sky. Its primary advantage in the hunt for quasar secrets is its incredible sensitivity to infrared light. Why does this matter? Because the universe is expanding. The light from the most distant quasars has been stretched or redshifted from its original visible and ultraviolet wavelengths far into the infrared part of the spectrum. For Hubble, this light was often too faint and too red-shifted to detect clearly. JWST, with its massive gold-coated mirror and suite of sophisticated infrared instruments, is built specifically to catch this stretched light. It will allow us to peer directly into the cores of quasars from the universe's infancy, witnessing their formation and early growth phases in unprecedented detail. We will be able to map the structure and temperature of the accretion disks themselves, looking for the telltale signs of instability or perhaps unexpected order. We might even be able to trace the flow of gas as it spirals inward, effectively creating a movie of the feeding process that fuels the cosmic beacon. Simultaneously, on the ground, a revolution is brewing in radio astronomy. The Square Kilometre Array, or SCAR, is not a single dish but a vast network of thousands of radio antennae spread across South Africa and Australia. When fully operational, its collective collecting area will be, as the name implies, approximately 1 square kilometre, making it the most sensitive radio telescope ever constructed by humanity. Its role in deciphering the Quasar Enigma will focus on the jets. Current radio telescopes can see these jets, but to the SKA, they will appear in hyper-sharp resolution. It will be like switching from a standard definition television to an ultra-high definition 8K display. the SKA will be able to detect incredibly faint, complex structures within the jets, knots, helices, and shock fronts that are currently invisible. It could measure the magnetic field lines within the jets with exquisite precision, testing our magneto-hydrodynamic models to their limits. Most intriguingly, its sensitivity might allow it to detect extremely low-level, complex modulation in the radio emission from these jets. If there were any intentional, information-rich pattern superimposed on that natural roar of energy, the SKA would be the instrument most likely to find it. This two-pronged observational assault is our best hope for finding what scientists call a smoking gun. For the natural cosmic engine hypothesis, the smoking gun would be the confirmation of predictions. JWST might observe the predicted turbulence and clumpiness in the accretion disks of early quasars, exactly as our simulations suggest. The SKA might reveal jet structures that perfectly match the most sophisticated MHD models, with no anomalies that require new physics. This would be a triumphant validation of our understanding, closing the book on the artifact hypothesis by demonstrating that nature, left to its own devices, is fully capable of creating such precise and powerful phenomena. Conversely, a smoking gun for the artificial construct idea would be the discovery of something profoundly inexplicable. What if JWST, while staring at the heart of a quasar, detected a luminosity that was perfectly, unnaturally stable over millions of years, defying the natural flickering of chaotic accretion? What if the SKA, while mapping a jet, found a section where the magnetic field was organized in a geometric, crystalline pattern that no known natural process could generate? Or what if it decoded a series of pulses from the jet's base that matched a complex mathematical sequence? Such a discovery would be earth-shattering, forcing an immediate and complete re-evaluation of our place in the cosmos. The data from these new telescopes will not just add to our knowledge, it will actively test the boundaries between natural law and potential engineering. We are on the cusp of moving from speculation to evidence-based conclusion. The universe has held its secrets for billions of years, but with these new tools, we are finally building the keys to the lock. This brings us to a deeply philosophical crossroads, one that forces us to question the very definition of a message and the limits of our own perception. We've explored the staggering physics and the potential for both beacons and weapons, but now we must confront a more subtle challenge. If a quasar were an artificial beacon, how on earth would we actually recognize it? Our entire approach is inherently, unavoidably human-centric. When we imagine an advanced civilization trying to communicate, we instinctively picture a refined version of our own technology, modulated radio waves, precisely timed laser pulses, or complex mathematical sequences imprinted on a carrier signal. This is a projection of our own desires and capabilities onto a universe that may operate on entirely different principles. A Type 3 civilization, one that commands the energy of a galaxy, might have no need for such intricate subtlety. For them, the ultimate statement of presence might be sheer, unadulterated luminosity. The quasar itself, in its raw, broadband, roaring glory, could be the message. Its simple, enduring existence, shining across billions of light years, might be the most efficient way to scream, "We are here," into the cosmic void. There would be no need to encode a complex message about biology or mathematics. The message is the medium itself. The ability to create or control such a phenomenon is the only credential that needs to be presented. It's the cosmic equivalent of building a pyramid so immense that it can be seen from the moon. The structure itself is the announcement, a testament to power and existence that requires no accompanying plaque or instruction manual. This idea fundamentally challenges our search for narrowband, information-rich signals. We might be listening for a whispered conversation while the universe is shouting a single, monumental word. Furthermore, we must grapple with the humbling possibility that the beacon isn't meant for us at all. our assumption that a signal would be designed for a nascent species like ours is arguably another form of cosmic arrogance. The intended recipients could be other civilizations of a similar transcendent level, for whom the quasar's specific properties, its exact frequency profile, its stability, or its position relative to galactic magnetic fields constitute a rich data stream. Or the purpose could be entirely practical and inward-facing. An advanced culture might use these objects as the foundation of a galactic navigation network, creating a fixed set of reference points for travel or communication across unimaginable distances. In this scenario, the quasar isn't broadcasting a hello to anyone. It's functioning as a piece of essential infrastructure, a cosmic lighthouse ensuring that their own ships don't get lost in the dark. We would be like a remote island tribe discovering a flashing buoy off their coast, completely unaware that it is part of a vast, sophisticated shipping lane system that has nothing to do with them. We might study its flashing pattern, trying to decipher a message meant for us, when in reality, we are merely observing a functional piece of technology whose purpose and language we cannot comprehend. This leads to the most profound and unsettling conclusion of all. Our inability to recognize a signal does not mean it isn't there. It might simply mean we are like a person who has never learned to read, holding a beautifully written letter. The information is present, clear and unambiguous to those who understand the script, but to us, it remains an indecipherable pattern of ink on a page. The universe may be teeming with communication, with beacons blazing in plain sight, but we lack the conceptual framework, the fundamental vocabulary, to even begin to interpret them. The great silence we perceive may not be silence at all, but a conversation happening on a frequency we cannot yet tune into, written in a language of energy and gravity we have not yet learned to speak. Shifting our perspective from conquest to conservation opens up a fascinating and perhaps less terrifying possibility. What if the activation of a quasar isn't an act of aggression, but one of ultimate defense? In this refined view, the quasar isn't a cannon aimed at an enemy. It's a shield, a monumental piece of cosmic engineering designed to carve out a safe harbor in a dangerous and unpredictable universe. The sheer energetic output that we perceive as destructive could in fact be a meticulous act of cleaning and fortification. Imagine a civilization that has achieved a level of stability and prosperity within its home galaxy. Their primary concern is no longer expansion but preservation. The cosmos, however, is filled with natural threats. Dense clouds of cosmic radiation, wandering rogue black holes, or even the relentless flux of high-energy particles from nearby galactic mergers. To protect their sprawling interstellar civilization, they might need to manage their local environment on a scale we can barely conceive. A quasar's relativistic jets could serve as the ultimate cosmic broom. By carefully aiming these beams, such a civilization could sweep clear a vast volume of space, pushing out or dissipating dangerous concentrations of interstellar gas and radiation that would otherwise pose a constant threat to their worlds and travel routes. They could be creating a sterilized, high-energy buffer zone around their galactic territory, a region so energetically hostile that it becomes a natural deterrent. Any ship or probe attempting to cross this barrier would be subjected to an unsurvivable bath of radiation, effectively making the civilization's domain a fortress without walls. This transforms the quasar's function from one of invasion to one of isolation and protection. The concept becomes even more compelling when we consider the universe's most mysterious component, dark matter. We know this invisible substance forms halos around galaxies, but its true nature and potential hazards are completely unknown to us. What if certain densities or interactions of dark matter are harmful to complex life or advanced technology? A civilization that has decoded the physics of dark matter might learn to use a quasar's immense gravitational and energetic influence to literally scour their local galactic neighborhood. By manipulating the accretion disk and jets, they could disrupt the dark matter halo, dispersing it or altering its distribution to create a safe, clear bubble within which their civilization can thrive without unseen subatomic interference. This isn't about destroying other life. It's about perfecting their own environment, a form of galactic-scale terraforming that uses the most powerful tool available to ensure long-term survival. The level of control this implies is, of course, mind-boggling. It means being able to ignite and then precisely regulate a supermassive black hole, to aim its jets with astronomical precision over millions of years, and to understand the complex feedback loops between the quasar's output and the galactic ecosystem. This defensive application, while less sinister than an offensive weapon, still places the civilization wielding it firmly in the realm of the Type 3 Kardashev scale. They are no longer inhabitants of their galaxy. They are its stewards and architects capable of manipulating its very core to serve their needs. The quasar, in this light, ceases to be a symbol of destruction and becomes one of profound, disciplined power, a tool not for war, but for crafting a permanent and protected home in the stars. To truly grasp the scale of this cosmic power, we need to anchor our theories in the raw data of specific, extraordinary objects. Let's focus our attention on Ton 618, a hyperluminous quasar so immense it redefines our understanding of what is possible. At its heart lies a supermassive black hole with a mass measured at a staggering 66 billion times that of our Sun. To put this almost incomprehensible number into perspective, if you were to replace the Sun at the center of our solar system with this behemoth, its event horizon would extend well over 1,000 times the distance from the Sun to Pluto, engulfing our entire system in an abyss of gravity. The energy this object radiates is so vast that calling it a trillion suns feels almost inadequate. It is a constant, raging storm of light and radiation, a singularity of such overwhelming power that its very existence challenges the upper limits of black hole growth models. Now consider S50014 plus 81, another titan that pushes the boundaries of physics in a different way. Its luminosity is so ferocious that astronomers theorize its accretion disk is consistently pushing against what is known as the Eddington limit. This is the theoretical maximum stable luminosity a black hole can achieve, the point where the outward pressure from its own radiation perfectly balances the inward crush of gravity. If a black hole tries to exceed this limit, the radiation pressure should, in theory, blow away the surrounding accretion disk, effectively cutting off its own fuel supply. Yet, S50014 plus 81 seems to persistently operate at or near this extreme boundary, suggesting a feeding process of almost perfect, sustained chaos or perhaps a level of stability that defies our standard models. These are not just slightly more powerful versions of ordinary quasars. They are the outliers, the cosmic champions of raw energy output. If any phenomenon in the universe were to be co-opted or engineered for a specific, grand purpose, these extreme examples would be the prime candidates. Their sheer power makes them the only plausible engines for projects of galactic-scale engineering. The energy required to send a coherent signal across billions of light years or to power a jet capable of influencing another galaxy is available here in abundance. This makes their unique properties, their jet structures, their variability patterns, and the stability of their incredible output critical data points in our search for anomalies. For instance, does the jet from Ton 618 show any peculiar, non-random wobbling over time that could hint at directional control? Does the light curve of S50014 plus 81 exhibit a stability so perfect that it seems to smooth over the natural turbulence of an accretion disk? These are the subtle clues that next-generation telescopes like the James Webb Space Telescope and the Square Kilometre Array will be searching for. They will scrutinize these titans with unprecedented resolution, looking for any signature, however faint, that cannot be explained by the untamed laws of physics alone. These objects are and will remain high-priority targets, not just for understanding the limits of nature, but for testing the ultimate boundary between a natural cosmos and one that might, just might, bear the fingerprints of a timeless intelligence. So where does this leave us after journeying from the turbulent hearts of distant galaxies to the speculative edges of cosmic engineering? The evidence, when weighed carefully, presents a compelling, if not entirely settled, case. On one side of the scales rests the natural explanation, a model built over decades of observation and refined by sophisticated computer simulations. This view tells a coherent and elegant story of galactic life cycles, where quasars are the brilliant, fiery adolescents of galaxies. They are the natural outcome of gravity's relentless work, a self-regulating mechanism born from the chaos of galactic collisions and the inevitable collapse of matter into supermassive black holes. This explanation requires no exotic assumptions. It operates entirely within the well-tested laws of physics as we understand them. It accounts for the flickering, the jets, the immense power, and their prevalence in the early universe. It is a powerful, parsimonious, and deeply satisfying scientific narrative that aligns with virtually everything we have observed. And yet, the other side of the scale holds a profound and lingering question. The natural model, for all its explanatory power, does not, and indeed cannot completely rule out the possibility of an artificial origin. The absence of evidence is not evidence of absence, especially when confronting a technology that could be billions of years more advanced than our own. The very perfection of the natural explanation could be its most clever disguise. When we scrutinize the case for the beacon hypothesis, we find it facing its toughest challenge in the persistent silence. Our most sensitive searches have found no intelligently engineered signal hidden within the roaring broadband static of a quasar's light. The fluctuations are chaotic, the quasi-periodic oscillations explainable by orbital resonances, and the overall behavior fits the profile of a natural, if extreme, physical system. A civilization intending to communicate would likely choose a more information-rich, efficient method than disguising a message in what appears to be pure astrophysical noise. This lack of a clear, decipherable signature is a significant point against the idea of quasars as deliberate lighthouses. The weapon hypothesis, by contrast, aligns more naturally with the raw, observable facts. The sheer, unadulterated destructive power, the focused jets capable of sterilizing entire galactic sectors, the longevity that allows for sustained environmental engineering, these properties fit the profile of a tool for galactic scale management, whether for gardening or for war. The energy is precisely where you would expect it to be for a civilization operating at the peak of the Kardashev scale. However, this theory also stumbles on a critical lack of evidence. We see no clear sign of targeting or use. The jets of the quasars we observe are not systematically aimed at other galaxies or life-bearing regions. They point in random directions, as one would expect from natural processes governed by the random spin of black holes and the chaos of accretion. Without a single, unambiguous example of a quasar being manipulated, a jet swiveling on a cosmic timescale to track a target, or an outburst triggered in a galaxy with no discernible fuel source, the weapon idea remains in the realm of compelling but unproven speculation. Therefore, the most scientifically honest and probable conclusion is that quasars are exactly what they appear to be: magnificent natural phenomena, the universe's way of building and regulating its largest structures. They are not the artifacts of ancient gods, but the fiery forges where galaxies are tempered. Yet, to stop there would be to miss the entire philosophical point of the exercise. The true value of the Quasar Enigma is not that it proves the existence of other intelligences, but that it forces the question upon us with unavoidable urgency. Their very existence, natural or not, demonstrates the upper limits of power and engineering that the laws of physics permit. They show us that the universe is capable of producing energies and structures so immense and precise that they are functionally indistinguishable from the products of a supreme technology. Quasars present us with a cosmic Rorschach test. In their brilliant, distant light, we see reflected our own hopes for connection, our fears of a dangerous cosmos, and our profound curiosity about what might be possible. They teach us that the line between the natural and the artificial may be far blurrier than we ever imagined, and that the ultimate signature of intelligence in the universe might not be a whisper in the static, but the awesome, humbling, and silent demonstration of a mastery over reality itself. So, after this incredible journey across space and time, we are left staring into the light of these distant titans, grappling with the ultimate question. Are they cosmic lighthouses guiding the way, or are they the ultimate weapons of galactic-scale conflict? The honest answer, the one that science demands, is that we still do not know for certain. The natural explanation, that quasars are the brilliant, fiery adolescents of galaxies, powered by the inevitable gravitational collapse of matter into supermassive black holes, is overwhelmingly compelling. It is a story that is elegant, self-consistent, and supported by a vast and growing body of evidence, from the flickering of their accretion disks to the precise alignment of their jets with our models of magnetohydrodynamics. To declare them artificial would require a level of proof that so far remains utterly elusive. And yet, the sheer, humbling scale of these objects, the almost perfect efficiency of their energy conversion, and their mind-boggling longevity force us to keep that door of possibility open, if only by a crack. Perhaps the true, lasting value of the Quasar Enigma is not in delivering a final answer, but in the profound journey of inquiry it inspires. It pushes the very boundaries of our imagination, forcing us to contemplate realities where the line between a naturally occurring phenomenon and a deliberately engineered artifact becomes blurred beyond all recognition. It challenges our anthropocentric assumptions about what a message should look like, or what a weapon could be, urging us to think on timescales of billions of years and energy budgets of entire galaxies. This mystery compels us to ask bigger, more fundamental questions about our own fragile place in the cosmos. Are we the lone conscious audience in a silent, mechanical universe, or are we simply late to a conversation that has been raging since the cosmos was young, a conversation whose language we have not yet learned to speak? The light from a quasar is a fossil, a snapshot from an era long before our planet even formed, and in its ancient glow we find a mirror reflecting our own deepest curiosities and fears. We project our hopes for connection onto the idea of a beacon, and our anxieties about a dangerous cosmos onto the specter of a weapon. In the end, the quasar may be the ultimate cosmic Rorschach test. What we see in its brilliant, distant heart says as much about us and our yearning to understand as it does about the object itself. So we turn the question over to you, because this is a mystery that belongs to all of us. When you look up at the night sky and contemplate these points of light that outshine galaxies, what do you believe? Are we witnessing the universe's most formidable natural power plants, or are we gazing upon the cooled, dormant artifacts of beings whose power and purpose we can scarcely imagine? Share your most compelling theories and thoughts in the comments below. We are genuinely excited to continue this conversation with you. And if your curiosity about the universe's grandest mysteries is as unquenchable as a quasar's hunger, be sure to subscribe for more deep dives into the wonders that lie just beyond the edge of our